Hey everyone. Today I want to continue our study of cyclic groups. And so let's start off like this. So let's let A and B be natural numbers. And what I want to look at, so we'll say, and consider the set capital H, and we're going to define it like this. So it's the set of all things of the form A, what symbols do I want to use? M. Yeah, M times A plus N times B, where M and N run through all integers, right? So we started off with a couple of positive integers, A and B, right? Those are the natural numbers. And then we look at all possible expressions of this form. So integer times A plus integer times B. And notice, right, since everything here is an integer, M, A, N, and B are all integers, this is a subset of the integers, right? So now it's easy to check. So let's say it is easy to check that H is actually a subgroup of Z, right? So I'll let you do that, or I'll leave that as an exercise. Just use the subgroup test to actually verify that. And so now, what do we know? Well, by our previous result, which was corollary 6.3, so by corollary 6.3, we know that H is cyclic, right? Subgroups of cyclic groups are cyclic, and in particular, we know what subgroups of Z look like. They look like multiples of N, right? We left off something last time where the subgroups of Z look like that of the form N times Z. Okay, well, knowing that this object right here, this set right here, actually is a subgroup, leads to a certain definition. And so that's where we're headed. The greatest common divisor of the positive integers say little a and little b is the positive generator little d of the cyclic subgroup, and let's write it out. So it would be the subgroup generated by D, which is the set of all things of the form A, how do I write it? MA plus NB, where M and N run through all integers. Now, this definition right here is definitely not the one that you see, or I'm going to say most likely not the definition that you see in your number theory class or in other classes where you've learned about greatest common divisor, right? But this definition is definitely useful for theoretical purposes. It's equivalent to the definition that you learn in your other classes, right? But from an algebraic standpoint, this is the one that we want to work with. So let's just kind of talk about this for a second. So we're defining the greatest common divisor, right? That's going to be some positive integer. And the way we're defining it is we're saying, all right, take your integers a and b, look at all possible expressions of this form, ma plus nb. We know that that is a cyclic subgroup of the integers. In fact, let's write that over here, right? This is a subgroup of z. We know that subgroups of Z are cyclic, as we said over here, and so there has to be a generator. In fact, any subgroup, any cyclic subgroup has both a positive, any cyclic subgroup of Z has a positive generator and then its twin, the negative generator, right? So, for example, the subgroup generated by 2 is also equal to the subgroup generated by -2, right? So the element and its inverse both generate the same cyclic subgroup. So right here, this group right here actually has 2 different generators. We choose the positive one, right? And we call that number the greatest common divisor of A and B. The notation. So notation is the usual thing, G, C, D of A, comma, B. If GCD of A and B equals 1, we say that A and B are relatively prime. So there's a piece of terminology that you've probably heard before. So relatively prime just means GCD of A and B are equal to 1. Now, we will need this fact right here. So lemma, let's call it lemma 6.4. This is often referred to as Euclid's lemma, or it's really a generalization of Euclid's lemma. But so just if you may have seen this, Euclid's lemma. Right, some people refer to this as Euclid's lemma. And so it goes like this. If A and B are relatively prime, and let's say A divides B times C. Is that what I want? Yeah, A divides B times C. Then, then A has to divide C. Right, so this is a fact. You may have learned this in a number theory class, maybe even a combinatorics class. Right, if A divides this product right here, B times C, and you know that A and B are relatively prime, then A has to divide the other factor. So let's prove this. Now, we've said that A and B are relatively prime, right? Which means then, well, it means this. So let's let M and N and Z be such that MA plus NB is equal to 1, right? Since the greatest common divisor in A and B, so let me just off to the side here, let's remind you. So what we know is that since the greatest common divisor is equal to 1, when we look at the set of all expressions, MA plus NB, where M and N run through all of Z, right? So the GCD of A and B is defined to be the positive generator of this. Since we've said the GCD is equal to 1, we have that. And so what does that mean then? Well, 1 lives in this set right here, which means that 1 has to be expressible in this form right here. If 1 is one of these objects right here, then 1 has to be written this way. So we have an M and an N for which this equation right here is true. Now what else do we know? We know that A divides BC. So let's say and let T in Z be such that AT is equal to BC. All right, so I've used the 2 statements that we have here, the 2 facts. We know that A and B are relatively prime. That's this first part, and then we know that A divides BC, so we have the second part right here. Okay, now what's the goal? We want to show that A divides C, which means that we need C to be a multiple of A. So let's do it like this. So then A times Cm plus Tn is equal to, all right, so I'm going to multiply things out here. This is ACm plus ATN, just distributing. And then, let's see, what do I know? AT, that's equal to BC, so this is ACM plus BCN. And then if I factor a C out, let me write it up here. So this will be equal to C times AM plus BN. But what do we know about what's inside the parentheses? That's equal to 1. So this is equal to C times 1, which is equal to C. So what do we have then? We have A times this integer right here is equal to C. A times an integer equals C. We could say, therefore, A divides C. That's kind of a nice proof. Now, I mean, there's a little bit of a trick here, right? We had to come up with the right integer, right? So you kind of have to play around with things a little bit. And you can think of it as kind of reverse engineering, right? I know that I need C times 1 equal to, or I need A times something equal to C. The trick was to write 1 in this special way and then undo things until we figure out how to factor an A out. Right? So there's the idea behind the proof. Okay, but now that we have this fact, and we'll need this fact later on, and now what we want to do is continue studying, right? We kind of want to learn more about the structure of cyclic groups. So that's where we're headed now, structure of cyclic groups. So let's start off with a cyclic group. So let's let G be cyclic with generator little g. And I just kind of want to talk about, let's just have a discussion about what we can say. So there's two possibilities. I want to consider these two possibilities separately. One possibility, right, when we have a generator, that the order of that generator could be infinite or it could be finite. And I want to look at those two cases separately. So case one, let's look at the situation where the order of our generator is infinite. So what does that mean then? It means that the cyclic subgroup generated by G has an infinite number of elements, right? So in this case now, so let's say suppose that G raised to some power is equal to the identity, right? And I should say, for some S not equal to 0. Of course, G to the 0 is equal to the identity. So suppose that we have some non-zero power of G equal to the identity. Well then, if we look at the cyclic subgroup generated by G, what's that going to give us? Well, it's going to tell us, and I should say it this way, it's going to be contained in the set of all things of the form, what's it going to be, let's use G to the I, where I is between plus and minus S. So here's the idea. You take G, you look at G to the 0, G to the 1, G2, so a little bit of just scratch work here. If you look at G to the minus S, G, and then G to the 0, G, G squared, all the way up to G to the S. That's this set right here. And so if g to the s is the identity, right, then this becomes an identity. And then what happens if you do g to the s plus 1, that gives you g again. And then g to the s plus 2 gives you g squared. So as you raise g to various powers, the only options are going to be these elements right here. And now, notice this, so this subgroup is contained in here, and this is a finite set, so which is finite, but we know that that's impossible. The subgroup generated by little g is actually an infinite set, so there's no way it can be contained inside this finite set, right? So this is a contradiction. And so what does that tell us then? It is impossible for a non-zero power of g to be equal to the identity, right? So it follows, right, so yeah, let's say it this way. Thus, g to the s equals the identity if and only if s equals 0. Now, as a consequence, and this is really what we're getting at, so as a consequence, if let's say that we have the situation, let's say k and m, so as a consequence, if g to the k is equal to g to the m for some k and m and z, right? So suppose that we have some powers, a couple of powers of g, equal to each other, then by multiplying by inverses, what we would get is g to the k minus m equals the identity. I multiplied on both sides by g raised to the minus m. And so, according to our computation up here, k minus m has to equal 0. Oh, I should say, and so, k minus m equals 0. Okay, so what does that tell us then? So let's write it like this. This is really the conclusion that we were headed for in this case 1 discussion. Thus, g to the k equals g to the m if and only if k is equal to m. Okay, so now let's look at case 2, and that's going to be the case that we have a finite element. So case 2 is that the order of g, let's say it's equal to some number n. Okay, now what we did is we've in the infinite case, we've shown that two elements can be equal if and only if their exponents are equal. So if you see g to the 7 and g to the 12, and you are in a group where the generator has infinite, cyclic group where the generator has infinite order, you're guaranteed g to the 7 is not equal to g to the 12, right? Can't happen. But now in the finite case, it's maybe a little bit more complicated. So now we've got our second case, order of g equals n. So since g, since the subgroup generated by g is finite, there exist integers, and in fact I should say distinct, so there exist distinct integers, let's call them s and t, so there exist distinct s and t in z, such that g to the s is equal to g to the t. So the situation that occurs in or the situation that we had in the infinite case right? Where you cannot have g raised to two distinct powers and then have them equal. This actually occurs all the time in a finite group. And the reason here, so what am I using here? This is just the pigeonhole principle. All right, we've got a finite group. We have a whole bunch. We've got an infinite number of possible powers, right? We can do g to the s, g, we can do all possible powers. Let's say g to the all possible powers g to the k, right? Because this subgroup right here is finite, there are going to be repeats. So there's going to be a g to the s and a g to the t that give us the same element. So it follows that g to the s minus t is equal to the identity. Yeah. So in particular, there exists a smallest, say m in n, so some natural number, such that g to the m is equal to the identity. So what did I just use here? I just used the well-ordering principle. So what's going on here? Look at all possible positive integers for which g raised to those integers gives you the identity. You're guaranteed that there's at least one, and so now that allows us to apply the well-ordering principle. Just take the smallest one for which g raised to that power is equal to the identity. We're guaranteed that it exists by well-ordering principle. So if m is strictly less than n, then if you look at the cyclic subgroup generated by g, it's going to look like this. There'll be the identity, there'll be g squared, up to, well, it'll really be g to the m minus 1. And so, the order of little g is equal to m, which is strictly less than n. That's a contradiction, right? Because we said that the order of g is equal to n. Okay, so that can't be the case. And so what does that tell us then? Well, okay, so a similar argument, so we'll say similarly, m greater than n gives a contradiction, right? So what does that force us to conclude? It tells us that m has to equal n. So conclusion is that m has to equal n. And so this gives a nice, a nice alternate characterization of the order of an element little g. So we can say thus, the order of g equals n, right? This number n is the least positive integer such that g raised to the n is equal to the identity. So this is definitely something you want to focus on. Oop. Right? All right, so that's important. There's an alternate characterization of the order of an element. So now, still working in this same case, right, where the order is finite. So now, suppose that g to the t equals the identity for some integer little t. Now I'm going to apply the division algorithm. So applying applying the division algorithm, what we get is, so I want to express t, so t is equal to n times q plus r, where q and r are integers, and we know that r is strictly less than n. All right, so what does that tell us? So now we have the identity is equal to g to the t, which is equal to g to the n q plus r, which is equal to g to the n raised to the q times g to the r. Now what do we know about g to the n? Well, we know that g to the n is equal to the identity. So this is equal to identity times g to the r, which is g to the r. So what does that force us to conclude about r? Well, since r is strictly less than n, and n is the smallest positive integer that gives us g raised to that power equals to the identity, that forces us to conclude that r has to be 0. This implies that r equals 0. Okay, so what does that tell us then? Well, we said that g to the t is equal to the identity, and in the end then, what did that force us to conclude? It forced us to conclude that t is a multiple of n. So, in other words, g to the t is equal to the identity if and only if n divides t. Okay, and now, so let's write down our characterization now of how elements behave in a cyclic group of finite order. So, conclusion. What would happen, or when can this happen? We have a couple of elements, g to the s and g to the t. If they give us equal elements within our cyclic group G, right, so this will occur if and only if n divides the difference s minus t. Okay, so this gives us the difference in terms of it tells us how elements behave differently when we're in an infinite cyclic group versus a finite cyclic group. In the infinite case, the only time we can get equality is if those exponents are equal. In the finite case, we can get equality if and only if the n, the order of our group, divides the difference of those exponents. Okay, so let's summarize the discussion that we've had so far. And so summarizing, and I want to call this, we're going to call this lemma 6.5, and it's going to take all of what we've done in this last discussion and put it in one place. So let's let G be a cyclic group with generator G. And so then, considering the two cases, the case A, right, if the order of little g equals infinity, right, then g to the s equals g to the t if and only if s equals t, right? So in the situation where we have a generator that has infinite order, when you look at powers of elements, it's very easy to tell whether they represent the same element. The exponent's either the same or it's not, and they're only representing the same element if the exponents are the same. Now for part B, so if if the order of G equals n, then G to the S equals G to the T if and only if n divides S minus T. And in that discussion we had a little bit more. We got another characterization of what the order of the element is. And so we'll just have a little add-on here. So moreover, the order of G, moreover n is the least positive integer for which G to the n equals the identity. So it's the first positive integer for which, when you raise G to that power, you get the identity. Okay, so now let's see what else I want to talk about. Ah, yes. Okay. So let's just remember back to what we were talking about when we first introduced binary structures. So let's say recall binary structures let's use these symbols. So S star and T comma dot are isomorphic. If, let's use the symbol, I guess I use the symbol phi. So if there is a bijection, capital phi, from S to T such that phi of x star y is equal to phi of x dot phi of y for all x and y in capital S, right? So an isomorphism, right? This map here is called an isomorphism, this function called an isomorphism. And so what is, it's a bijection that respects the operations in the two different binary structures. Now, in the case that S and T are actually groups, right? So we defined isomorphism for binary structures, and so we can say the word isomorphism even in the setting where S and T are not groups, right? But we're really interested in the group situation. So in the case that S and T are groups, we write, so the symbol that we'll use is a little equivalence bar, so it's a double tilde. And so this symbol, right, means you would read this, S is isomorphic to T. And in this situation then, right, so such groups have the same, let's say identical algebraic properties. So really then, an isomorphism is just a process of renaming the objects, right? You call them something in S, just give them new names in T, but from an algebraic standpoint, you can't tell the difference between isomorphic groups, right? They give you exactly the same properties. And so now at this point, we don't have a whole lot of, we don't know that many algebraic properties, but we'll see as we go along more and more algebraic properties, and an isomorphism is one that preserves all of them. Okay, so our next result, and this is going to involve an isomorphism, so this will be theorem 6.6. So let's let G be a cyclic group with generator little g. Little g. So two parts of this theorem depending on the order of our generator. So part A, so if the order of little g is equal to infinity, then G is isomorphic to the integers. Part B, if the order of G is equal to n, then we don't want to use. Yeah, okay. So then G is isomorphic to Z sub n. That's a big theorem. That's a big result. Because what it tells us here is that the group of integers is the prototype infinite cyclic group, right? Every infinite cyclic group is isomorphic to the set of integers. So when you think of infinite cyclic groups, you can immediately think in terms of the properties that the integers have. It also says that the order n cyclic group is isomorphic to Zn. So Zn is the prototype finite cyclic group. Okay, so let's prove this. Right, but this is a big deal, right? What it does is it completely characterizes cyclic groups. Right, it's either infinite, in which case it's isomorphic to Z, or it's finite, in which case it's isomorphic to Zn for the appropriate choice of n. So for part A, yeah. So since G is cyclic, for each x in G, there exists, what symbol do I want to use? I guess a little k in Z, such that x is equal to G to the k, right? In a cyclic group, all elements are powers of the generator. Now, by our previous results, so by, this is lemma 6.5a, right, so our previous result, this one, this integer right here is unique. So this integer k is unique. I mean, what's going on here? It's impossible for x, if x is equal to G to the k and it's equal to G to the m or something like that. What did our previous lemma tell us? It tells us that m equals k. So that tells us that x can be uniquely written as G raised to a certain power of k. This tells us now how to define our function. So now we can define phi from, let's see what direction I want to go. We're going to go from G to Z. Phi of G to the K. That's what our elements look like. And I guess maybe I should use a different symbol. Do I want a different symbol? Oh no, I guess G to the K is fine. That's equal to K. Now, by uniqueness of representatives, right, there's exactly one way to represent each element as a power. And so this function right here is well defined, right? So by uniqueness, phi is well defined. Okay, so we have an honest function here. So now let's show that it's actually an isomorphism. So if phi g to the k is equal to phi of g to the m, then m is equal to n, so k is equal to m, then k is equal to m, and so g to the k is equal to g to the m. What does that tell us? That tells us that our function is 1-to-1. So therefore, or thus, phi is 1-to-1. Now to see that it's onto letting m be an element of z, we have phi of g to the m equals m, and so phi is onto. Now we need to show that it respects the operation. So now observe that phi of g to the k times g to the m, right? So we're going to multiply inside, and I don't really need to use that dot right there because we just use juxtaposition. So phi of g to the k times g to the m is equal to phi of g to the k plus m. Our function gives us k plus m, and that's exactly equal to phi of g to the k plus phi of g to the m. And so what does that tell us then? It tells us that phi respects the operation, right? In G, the operation is juxtaposition. In Z, we know that the operation is addition. Okay, so now I need to prove part B. I guess let me write a concluding sentence here. Therefore, phi is an isomorphism. Okay, now for part B, let's see. So since G is cyclic, for each x in G, there exists a little k in G, in Z, such that x is equal to g to the k. So once again, in any cyclic group, each element can be expressed as g raised to some power. The problem, not necessarily a problem, but remember, in part A, we had this uniqueness aspect going for us. In a finite cyclic group, we don't have the uniqueness. It's possible that, in fact, it will happen that this is true. There will be an x equals g to the k, and then it will also be equal to g to the m. In fact, there'll be an infinite number of integers for which x is equal to g raised to that integer. And so that will complicate things a little bit. So let's define phi from G to Zn by, well, we got to do the obvious thing. Phi of G to the K is equal to K mod n. Now, the first thing we have to do is we have to show that this function is well defined, and since we don't have uniqueness of representations, it's going to take a little bit of computation. So we will now say, suppose that g to the k is equal to g to the m. Now, what does that mean? So then by our previous lemma, is that 6.5? Yeah, 6.5. So by lemma 6.5, we have the n divides the difference, so m minus k. And so m minus k is equal to n times t for some integer t. So now, phi of g to the k is equal to k mod n, which is equal to, now if I solve for k, what we get is m minus n times t mod n, which is equal to m mod n minus nt mod n. And when you have a multiple of n and you do mod n, you get 0. So this part's equal to 0. And so this is equal to m mod n, which is exactly phi of g to the m. So what that tells us then is that phi is well defined. So therefore, thus, phi is well defined. So we have an honest function here. So suppose, we need to show it's 1-to-1 now. So suppose that phi of g to the k is equal to phi of g to the m. Then what does that mean? It means that k minus, k, what does it mean? K mod n is equal to m mod n. And so what does it mean? That means that their difference is a multiple of n. And so k minus m is equal to n times t for some integer t. That's what it means. I mean, that's what you get when two things reduced mod n are equal, then their difference is a multiple of n. So it follows that n divides k minus m, and so g to the k is equal to g to the m by lemma 6.5 part A. Therefore, phi is 1-to-1. It's pretty clear that it's onto for each I in Zn, note that phi of g to the I is equal to I, and so phi is onto. And then the last thing we need to do shows that our operation is respected. So so let's say now, if, or now, let me say if, now phi of g to the k times g to the m is equal to phi of g to the k plus m. That's equal to k plus m mod n. And then the nice thing about modular arithmetic, we can split this up into two pieces. So this is k mod n plus m mod n, and that's equal to phi of g to the k plus phi of g to the m. And one thing to notice right here, when I write that plus symbol right there or that plus symbol right there, both of those mean addition mod n. Right? I don't want to put a little subscript n there, but these both mean addition mod n. Therefore, phi is an isomorphism, right? And that's what we needed. Right, so that completes the proof. And so, I mean, this really is a big deal, right? It completely characterizes cyclic groups. If we want to know everything about cyclic groups, then all we need to do is study the integers and the integers mod n, so z and zn. Okay, so that's a good place to stop for today. We'll see you next time. This was fun. I wish this was in person, right? It would be even more fun if we could, kind of talk back and forth and you could ask questions. But we can't do that, so hopefully this is working out and you're actually able to learn from these lectures. Make sure to come to office hours and ask questions if you're falling behind or if you're unsure about a certain thing. Okay, see you next time.